So in general, my name is Ernest Kavea. I'm a third year student, majoring in electrical engineering, and I'll try to help you guys. Normally, I was supposed to be doing TDs with you, so I'll be doing more of TDs than cool because Mona is designed to take in the cool. So I read there was a concern. Somebody says that's a TD. So a TD is a travail dirigé. It's something like we'll be doing exercises, we'll be trying to solve some things together, yeah, and then try to see how able to analyze questions, probably as able to how if you are really understand, you'll be taught in code. I'm going to do one of the most simplest topics that I can say, and I can assure you, and that's numbers. So I'm going to deal with real numbers and complex numbers, and then we're supposed to do logic language based on some, but this is what she has probably already done this with SL in algebra. So I'm going to do this topic. We're going to move to suites, real, and complex. We're not really going to be going into details because of the time limit that we have. So we'll be just feeding you a little bit, and then it will be up to you guys to do a little bit. And then after that, we're going to look at functions. We're going to deal with limits that are stationary and limits that are continuing. And we'll be looking at some properties of limits. We'll further ahead do some deriving some functions. Functions that we can have, if we're more limited. We're going to be looking at comparison of sustained functions, asymptotes, all those functions, and then we're going to also look at formula data. So when, like we know, we have three types of formula data: 1, 2, and the third. So the third one is where we're going to bring in integration. Integration is the first part of Analyse 2. So there's some schools that start with Analyse 2. So answer Agadi, those that would want to go there, probably maybe be given same status with Analyse 2. So you're supposed to know integration. So I'm going to put integration on the formula data. We're going to look at integration, the Riemann, and everything, and then we're going to conclude everything in this. We're going to conclude the whole course in Développement Limité. Of course, the other topics that you're going to do when you go to school in Analyse 1, equation differential. Probably you're going to be doing that as you go to your schools, and then voila, bouger comme ça. Yeah, I don't know if there are any questions before we start.
No. You're not.
Okay. Okay.
We can start.
Oh, I have a question. Chapter 1 to 6, is this all semester 1?
And from chapter 1. Chapter 1, we have real numbers. Chapter 3, we have suites. Chapter 4, we've got what I'm going to teach you is actually semester 1. It's called Analyse 1. Okay, because Analyse is divided into normally Analyse 6, we've got Analyse 1, 2, 3, 4, 5, 6. So 5 and 6 normally people that do mathematical engineering around that grade, but normally in engineering school, you do from Analyse 1 to 4. Oh, sorry, I actually forgot. We have people that are doing business in here. So business, there will be points that I'll be taking to concentrate more, and there will be some topics or questions that will be solving. I'll tell you not to concentrate on them, okay? Because you guys are only work on a certain part, and then the engineering for you it's everything. So from topic 1 to topic 5, that's Analyse 1. So it's obligatory that you have to know everything. I don't know if I've answered your question. Have I answered your question?
Yes, you have. Thank you.
Okay. any other questions? I would really love it if it's possible. Elisha Ruben, can you help me at the end of the call? I would love to know those people that just to send you your course, your course, Ruben, so that when I'll be solving the TDs, I'll divide you guys into groups so that I kind of avoid to teach you things that are not really for you. Okay, so you should probably send your just your name and the list of probably Ruben is going to try to make some sort of like Excel where you're going to put your course. For example, if you want to go for ENSAM, APESA, EST, you can just give me a feedback. So, okay, me, I have 70% my so when you'll be doing the TDs, we're going to be doing more business. For the past few times, people have been saying you really give us a lot of stuff, but it's not really what we find that side. So I'm going to just teach you what you're going to find that side. Okay. So Ruben, you can please help me with that. And voila. We're going to, bon, this is already 1602. So we're going to just start, if there are no questions, we're going to start our first chapter. Okay, so our first chapter, we'll be looking at Nombre, Réel, et complex. What are your numbers, if I may ask? I really like pointing, so I'll be just pointing at random. Don't act like you've got bad Wi-Fi. Just answer me, please, so we'll play. We start with Alex. Alex, what are your numbers?
Real numbers, rational and irrational numbers combined.
Okay, rational and irrational numbers combined. Voila. So if there are rational and irrational numbers combined, how can you define what rational numbers are in English, in just common sense? I don't want you to exhaust your mind trying to think deep. No, just in general sense. How would we describe a rational number? If you hear something is irrational, what do you begin to think of? There's Body 2021. I believe Akainde is with us. Body 2021, I don't know who Body 2021 is. You can help us. What's a rational number? Body 2021. Unfortunately, it's quiet. Wadia Kaunda. What are rational numbers? How can you describe rational numbers?
A rational number is a number that can be expressed as a quotient or fraction, P or Q of two integers.
Didn't get you. You can repeat. Okay. I think I lost him. Okay.
A rational number is a number that can be expressed as the fraction of two integers.
Okay. Très bien. So we are saying it can be a number represented in African Sorry. I've actually been talking to my mic off. So on the scene for n, l'ensemble des entiers naturels. So I've got examples of natural numbers 0, 0, 1, 2, 3. So with these natural numbers that we have, for example, if we present these numbers, we say we've got n numbers. So n numbers that we have, we say it admits a success. It becomes success if we are going to be adding a 1 from this natural number that we have. So for example, we have a 0. 0 plus 1 gives you 1. 1 plus 1 gives you 2. That's what we are trying to describe here. So a natural number starts from 0 up to 1 with an increase of 1. So we say we admit all this to be n. So n with a consecutive increase by 1. So we'll be adding 1, 1, 1, 1, and there we are. We develop des entiers naturels real numbers. Of course, the question will come in. What if we want to have an exception? How do we note an exception in mathematics? We note an exception by using n étoile or n star. So n star, this indicates to say we can have these natural numbers, but don't include 0. C'est-à-dire les ensembles des entiers naturels non nuls. That is to say, you have this group of natural numbers except 0. For example, if you want, you can say, okay, I want to have natural numbers, but except 2. I don't want 2 to be part of my natural number that I'm going to be having in a given set. So I'm going to have n étoile, l'ensemble de n, strictement, you put your 2 there. C'est-à-dire que you don't want 2 to be included in your natural numbers. Okay, so that's what this is actually trying to say here. Étant dans deux entiers naturels x et y, on sait définir les ensembles. So we are given 2 natural numbers that we present by x and y. We've got x plus y. X can be 1, x can be 2, x can be 3. Y can be 1, y can be 2, y can be 3. We can say 1 plus 2 will give us 3, x minus y. Of course, we have to be very, very careful there. Real numbers, we said they are numbers that are given from 0 up to positive infinity. So you can't have a number that can be negative. If we look at a number that is negative, we develop to have an integer. And the integer, which is going to be the next type of number that we're going to be considering, which is just down here. So I've got x minus y. Ça veut dire que x obligatoire, ça doit être quelque chose qui est plus grand que y. Ça veut dire si on a x ici, c'est 3, on va dire 3 moins 2, because all those are real numbers. C'est la même chose ici. We have here x times y. If your x or your y in this situation, it should never be equal to 0. Why should never be equal to 0? Because every number that you multiply by 0, it gives you what? 0. So as long as you want to continue having a success, the n plus r, we have to put a consideration here. We shouldn't exaggerate by putting 0, because if you put 0, it's still going to be giving you the same reverse answer. Okay. And we also have a fraction x over y, where y is not equal to 0. Pourquoi? We have x is equal to y should not be equal to 0, because x over 0, it gives us what? It gives us any number over 0, it gives us what?
Excuse.
Yeah.
Like you are kind of fast before you can get clear.
All right. Are we okay?
Go.
Where is the question?
Like in fact, just start from the real numbers. You're fast, you know.
All right. Okay. So like I was saying, so we have real numbers. So real numbers, we are told that these are numbers that start from 0 up to probably positive infinity. So I've got 0, 1, 2, 3, 4, 5, up to positive infinity. Okay. So what is this set trying to say? So this set that we have here is trying to say we have natural numbers, we present them by a value n. Okay. So if we have this natural number that we present by the value n, the next number that we should have, or rather it's like a sequence. the next number that we get, we have to add what? We have to add a 1. Okay, so it's like a sequence. So I've got n plus 1, n plus 1. That's how we're going to be keeping on increasing. Putting to mind that n cannot be a consistent value. We can't have a constant value because if you're going to be adding chaque fois by 1, you're not going to be changing anything. So n can either be 0, n can either be 1, can either be 2, n can either be 3, etc. Okay, are we okay there?
Yeah.
Continue.
Okay. On note n étoile, this is to say there's an exception. If we have n étoile, this means we have an exception. So how do you represent this exception? If we don't want to include 0 in this set, we're going to say n étoile with an exception of what? Of 0. Voila, c'est easy. N with an exception of 0. So when you go to your school, you find that even exams, this comes, you find this something an exam. You give you maybe a sequence and then you say n sa 0. This means that we have got an exception. An exception that is to say 0. Means that in your set of natural numbers that you're going to be doing it, don't include 0. Okay. Ça va? Jusqu'à là?
Oui, ça va. But can they also use a different number?
Yeah, bien sûr. It's the same thing as saying I have a set of these pupils. There's Venzu, Blessed, and Blessings. Out of this set of Venzu, Blessed, and Blessings, as you invite people at a party, strict them all. Don't include Blessed. Okay, so I mean that you're going to say, okay, in this set of people that are going for my party, the exception is who? Blessed. Don't include Blessed in the venue. But of course, that's not to say every time that you want to have a venue, don't include Blessed. You can of course say, okay, this time around, I don't want Wenzu to be included. You delete Wenzu, and then you're just going to have Blessed and Blessings to come for a better party. It's just a description. If I want, I can say I want to have natural numbers, but please, with these natural numbers, I don't want you to include 2. Okay.
Oui.
Yeah, but of course we're going to try to enter into details to say that's a very good question. We're going to enter into details to say, but why in this in the statement that we have here, they have mainly focused on 0, and that is what brings us here. Okay, why have they mainly focused on 0 here? Well, they're focused on 0 because we have got x, for example, on étant donné des entiers naturels x and y, on sait définir le nombre. We have a problem with 0. 0 always gives us a problem in the sense that every time you are going to have a number here, like for example, if x is going to be a 0, usually you are going to have a repetitive number. If your y is 1, it's going to still be 1. If your y is 2, it's going to be continuously to be 2. No wonder normally when you're operating with natural numbers, we have a restriction, and that restriction is 0. We avoid to not be using 0 so often because it gives you a recursive number. The same thing that we have here. If we have 0 here minus maybe 1, it's going to be negative 1. That's an integer. The same case that we have here. If we use 0 here, every time, chaque fois, it's going to be giving you 0, 0, 0, 0, 0. C'est la même chose here. If we have x over 0, and every time on y we put 0, it's going to be giving you infinity, 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 which is not even a natural number. So every time, even when you go to your school, you're going to observe that even when you start looking at streets, a lot of my questions will focus on a restriction of not adding 0. Why? Because 0 is a complicated number. 0 is a very, very complicated number. So even in natural numbers, we rarely add 0. We normally start with 1, 2, 3, 4, 5. But that would be would be another interest, or another interest of mathematics that would actually want to get to know why 0 is so complicated. 0 is a very, very complicated number. So normally on natural numbers, we rarely avoid to use 0 because of situations like this that we have down here. So that's why here we restricted more on the 0 value when you're trying to describe natural numbers. C'est bon?
Oui, c'est bon, c'est bon.
Okay. Est-ce qu'il y a des questions jusqu'à maintenant? Do we have any questions? I'll be very frank with you. If you don't understand this topic, we are going to have difficulties in analysis. This is the most important topic in analysis, because the next one, I'll just be dreaming and say natural numbers. If you don't understand what a natural number is, if you don't understand why we have an exception 0, it's difficult. It's very, very more difficult. So if you don't have any question in natural numbers, probably we're going to do some TDs, some questions. We're going to solve together. We're going to enjoy solving together questions. You begin to understand more and actually develop more ideas. Okay? Donc, on remarque que l'addition et la multiplication, l'addition ici et la multiplication qui est ici, sont des opérations qui ont le résultat d'un nombre entier. Par contre, le résultat d'une soustraction ou d'une division n'est pas toujours un entier. So here we have, when we add the numbers and multiply numbers, no matter to have, but have a subtraction always gives you a natural number. So what this can be given, for example, when you are subtracting, we have what we call integers. What are integers? Integers, these are negative and positive numbers. So we have negative numbers, positive numbers. Okay, so I'm going to repeat that. When you are adding and multiplying, these operations will go to a positive, and when you're multiplying the number or they result into a natural number. But if you're subtracting or you're dividing, it's a different case. It gives you, it doesn't always give you natural numbers. So what does it give us? It gives us either integers, which is noted by that, qui est l'ensemble des entières relatives. On notera Z et 3. Pourquoi Z et 3? Toujours, with an exception of 0. Moi. Et what symbol is this? I taught this. What symbol is this? Teddy. What symbol is this? Teddy Mujimba. Teddy Mujimba, you are there, I can see you.
Yeah, I forgot them.
Ruben. This symbol. Ruben.
Yes, yes.
What is this symbol? Oh, you guys are forgetting mathematical symbols. We even used to use these symbols in Zambia. So it's not just in Morocco that we're using these symbols. Anyone who knows this symbol, the name of this symbol? Anyone?
I think it's
I think so for rational numbers.
Sorry? Sorry?
Rational numbers.
Rational numbers. Voila. Rational numbers. We are forgetting rational numbers. What are rational numbers? Rational numbers. What are rational numbers? Rational numbers is just number that we identify by using a fraction. For example, we have A over B avec A fois N, B fois N, où tout A appartient à l'integer et B et N appartiennent à la Z de 3. Pourquoi? Because here we cannot have these numbers, any of these numbers cannot be equal to 0. So you see the importance that we have here. We have A can belong to an integer, okay? A can belong to an integer, but B and N, pardon moi, should never be, can belong to an integer with an exception of what? Of 0. Okay. Voila. So we have, when we can use addition and multiplication to have real natural numbers, but it's not the same case when you are subtracting or dividing. So when you are subtracting or dividing, you can either have rational numbers or we can have integers. And we have an exception of integers, that this number should never be equal to, should never belong to, it can belong to an integer with an exception of 0. It should never include 0. B should never be equal to 0 because it's going to be giving you infinity always. C'est bon? Any
I've got a
questions?
question. Just
Yes,
a quick one. I have a question, a quick one. On the exception where you put a star, what's the spelling of the name, the trois, the Z, the trois? What's the spelling?
Étoile is E accent T-O-I-L-E. Étoile, it's just like star. Z star. Star in French is étoile.
Thank you.
C'est bon? Welcome, boss. Any other
I
questions?
have a question.
Yes, mademoiselle.
On this one where you're saying that the Q stands for rational numbers, and then we're saying there's alpha over theta. Is it alpha over beta? Sorry. Where there's A
No,
over
it's
B.
Yeah. A over B here.
Yes, no, here on top. Where there's
Here.
rational number, where there's Q.
Okay, yes.
So I was saying A
Here.
is a member of integers, but B
Voila.
is not a member of integers, with an exception of only 0 or any other exception or just 0.
Très bien question. So A is a member of integers. B is also a member of integers, except 0.
Oh, okay, thank you very much. I just wanted to clarify on the 0 part.
You're welcome. You're welcome. Feel free to ask questions. Make sure you understand each and every part. Mathematics is love. So if you don't have love in your heart, you can't have mathematics. Okay. Il faut aimer la mathématique. C'est ça. Any other question? Ninde? Any questions?
No question.
Okay. Everything's clear, right?
No.
Ok. On continue alors. On a bien attendu les inclusions suivantes. N inclut nombre naturel qui inclut les nombres rationnels. Inclusion. Inclusion mean, what does inclusion mean? Okay. What is if I say inclusion? The French graduates. What is inclusion? Samo Mumba. How would you define inclusion? C'est quoi les inclusions? Samo Mumba.
You mean I translate it into English? I think it means inclusion, like include something.
To include something, oui.
Subset.
C'est très bien. Subset, oui. Vous avez, why would you say it's subset? What's a subset? What's the subset?
It's a set within another set.
Très bien. So we've got n, which are natural numbers. I'm just reading through your comments right now. Am I still too fast? Because don't just write you're too fast if you're not able to ask me to say I didn't understand this part. So you have to tell me, am I still too fast?
No, that was before.
It was before. All right.
The current pace is just fine.
All right. Actually, I thought it's right now. Okay, so we've got n. These are the main numbers that we have. If we've got negative and positive numbers put together, what do we have? We have what we call integers. And out of integers, when you try to do some arithmetics with these integers, we begin to develop what? Rational numbers. So it's like the main The main boss is the natural numbers that we have, which spearheaded to deliver integers. And somebody sat down and thought, no, why should we just have integers? Let's include something that is maybe a fraction, and we develop a subset of rational numbers. Et les 4 opérationnels élémentales plus, moins et fois et en division peuvent s'attendre à l'ensemble rationnel des nombres réels. The same thing that I'm just from saying here, where we can have, maybe we can be adding something on top, subtracting something on top, or multiplying something on top, and then divide. We can afterwards adjust to say, okay, we have got a set of rational numbers. So, les Grecs classiques ont cru longtemps que toutes les quantités s'exprimaient par des nombres rationnels. Ils se sont aperçus que ce n'est pas toujours le cas. Enfin, on peut construire des nombres qui n'ont pas rationnels. Considérez par exemple un triangle. So, the Greeks had sat down for a long time and began to think, to say, okay, everybody has talked about natural numbers. Everybody has talked about integers. Everybody has talked about rational numbers. But can we really say that the last numbers that we can ever have or can belong on earth are rational numbers? They said, no. It's pas possible. So I said, okay, if that's not the case, then what can we do? How can we prove that there can be maybe an existence of rational number, other types of numbers, or maybe how can we add more spice? How can we spice up the rational numbers? Okay, so these people sat down and thought of trying to build up something like a triangle with the A, B, C sides. So I've got a triangle A, B, C. We've got the hypotenuse, the SOHCAHTOA, probably we know it, opposite and adjacent. Si on note A, which is A, which is the hypotenuse, la longue du segment BC, voilà, le segment, c'est ça, which is the hypotenuse, like I was saying. So we note A, the hypotenuse. B, c'est the CA, that of A and C. Voilà, we present this line by B. Et C, c'est the AB. We present this line by C, line AB by C. Alors, la théorème de Pythagore dit qu'on a la relation A au carré égalé à B au carré plus C au carré. The Pythagorean theorem, which says that we've got A squared is equal to B squared plus C, B squared, pardon, plus C squared. OK. Ainsi, on obtient que la longue de la diagonale d'un carré de côté B. So we note that B, okay, Ainsi, on obtient que la longue de la diagonale d'une carré de côté B égalé à C, qui est égalé à A. So we note that we've got the length that we have here of B, which is equal to C and is equal to A, est vrai à A égalé à square root of 2. So we note that if we, for example, suppose that A is equal to B is equal to C, and we suppose that B is equal to C, and this, all of it is equal to 1. That is to say, we have 1 here plus 1, which is going to be equal to 1 au carré plus 1 au carré, that's 2, 1, pardon. 1 plus 1 is 2. So for us to find the value of A, we're going to say A is equal to the square root of 2. Okay. Proposition. Very, very important. Like I said, we may have an exception. What is that exception? The exception that we're going to be considering now is the nombre au carré de. De is not a rational number. Square root of 2 is not a rational number. Probably you've done this proving in algebra, I believe so. So it's not something that I'm not really going to put into details, anything like that. Esther must have done a very, very good job on that. So we have an exception of rational numbers, which is the square root of 2. We demonstrate this nous allons faire une démonstration par l'absurde, where we suppose that square root of 2 is rational first of all. Every time we remember how we are doing proving by l'absurde, where we said the first thing that you have to do is you prove that it's rational. Il existe alors des entiers positifs A et B, tel que square root of 2 is equal to A over B. Si A et B sont pairs, on peut simplifier la fraction A sur B par 2. En simplifiant par 2 autant que possible, on arrive au cas où au moins des entiers A or B est impair. So we're going to, it's just some simple mathematics that we do there, where we suppose that square root of 2 is rational, and then we equate this to be A over B, and then we simplify this fraction by 2, and then we simplify again for the second time, where we arrive to say A and B are impair. En élevant au carré l'égalité, square root of 2 is equal to A over B, et en changeant les dénominateurs, on arrive à 2b squared is equal to a squared. But this is not very something that we should really get to concentrate on. Yeah, it's just how we prove that square root of 2 is not part of rational numbers. Like I said, there are actually exceptions that were put by the Greeks. Okay, so that's how we just the general view of square root of 2 is equal to that. Don't really put mind, you do that more in algebra. Now I'm not going to really focus on it, like I said. Okay, ask Esau, maybe if you haven't done it, just ask him the next time you have algebra. He's going to shed more light because that is going to do. I saw he posted something to do with recurrence parabsold etosa. So he's going to help you with that part. So we have other examples of irrational numbers. We have the pi, which is equal to this 3.14 constant, circumference, which is defined by like a circumference of a circle of diameter 1. The Nombre de Réel exponential function, which is equal to 2.718, la base exponentielle définie. Very, very important. We are going to look at this when we look at the more limited, how this came about. It's a very, very interesting function that we're going to have good time to look at. We also have the racine carré
Excuse me. I have a question. Can you please scroll up a little bit?
Okay. We are here.
No, again. Yeah. No. Down. Not that much. Where it's 2 pi squared or 2b squared.
2b squared. Okay. Yeah.
No, down below that fraction. Okay, there.
Yeah.
Yeah, that number in this one. How did the 2 still end up the other side, not as a fraction, but just a normal number, I can say?
Okay. So here what we have here, we've got square root of 2, right? Is equal to A over B. So in this square root, for example, square root, what's a similar number? Or how can we really say a square root? A square root is the same as saying 2 to the power 1 over 2 in a span.
See.
Oui. Bon. So if we're saying 2 to the power 1 over 2, how do we remove that 1 over 2, which is up there? We multiply it by 2. So if we multiply by 2, whatever you do this side should be done this side. So I'm going to say 2 to the power 1 over 2 times 2. And then here we're going to say A to the power 2 over B to the power 2. So we're going to cancel that. We're going to have 2 is equal to A squared over B squared. We cross multiply. We're going to have 2B squared is equal to A squared. C'est bon?
Oui.
Voilà.
But then the 2 is on top, but not below the A as a fraction.
Here. No, because
No, the
here
other
if
fraction below.
yeah, that's where
They're
I'm
not-
that's where I'm going. Because this
Okay.
fraction then come there from here. It comes from this expansion that we have here. Okay. Donc, if I say A is pair, okay, if A is in pair, on pair, because in this case I'm saying A is pair because you can have any number you can have, it's A squared, which is a pair number. So if A is in pair, means it's only got one certain digit number. On pair écrit, A is equal to 2A prime plus 1. Okay, so we present an impair number by saying we're going to look at functions. We're going to understand more advanced on the pair and impair numbers. So if A is in pair, we write A is equal to 2A prime plus 1. That is to say, if we have A squared here, we're going to say 2A prime plus 1, all this to the power 2. And it gives you A squared is going to be equal to 4A prime 2 plus 4A prime plus 1. It's the difference of two squares in span. It's 2A prime plus 1, this close bracket to the power 2. When you simplify this, it gives you this value that we have here. C'est bon?
Oui.
Qui est impair? So if we have this value that we have here, automatically it's impaired because we have an assumption that we have which is equal to this here, 4A prime plus 1. Just as I'm saying 2A prime plus 1. So it becomes impair. Séduit donc A est pair. Donc on peut écrire A is equal to 2A prime. So you can say A is equal to 2A prime.
I have a question. Where does the prime that you're talking about coming from, and what does it do to the numbers, and what does it mean?
Okay, so we bring in a prime here because of what A here, right? We can put A to the power X. A to the power. It's just like we're trying to separate this 2A. This A that we have here and this A. That's why the prime is coming about. Because if I were to say A here, it would just be simple. We take this A this side, we take that A side, and then you're going to solve the equation. Okay?
Continue.
Est-ce que c'est bon? Mademoiselle, est-ce que c'est bon?
No.
Okay, so I said we have got A is equal to 2A prime plus 1. We use A prime here because we didn't want to just use the same A that we have here. If we use the same A, you would easily find a solution. You just say, okay, since you have got A here and this A here, which is the same, take these two A and bring it here, and then you're going to A. So we made an assumption. We suppose we say, okay, what if we have an A prime? If you can use C, it's A to C plus 1. If you don't want to use A prime.
I understand where it's coming from.
Okay. I hope.
So what you're trying to say, like that thing doesn't add value to anything, or like that.
It's a supposition. You're supposing. When you're supposing something, it's just because you want to find an easy expression that you can use to find an original answer.
Excuse me.
Ok. Donc, on peut écrire A égalé à A prime, ce qui donne, so we have A prime that we have there, so which gives us 2B squared plus D A prime au quart.
Here.
Oui?
Yeah, like I had some problems with the connection, so I'm behind. Like starting on the
okay.
don't R squared, yeah. From there.
Okay. Donc A au carré, d'accord. Okay. So, like I was saying, you're okay up in this one. The 2B squared is equal to A squared, like I explained here. So the A squared here, we see that the A squared that we have here, because the main aim that we have here is, don't forget, what you're trying to prove is square root of 2 is not a rational number. Okay, so the first thing that you have to do is you have to prove that you have a value that you have, which is a squared here. A squared here is a pair number. But absurd, you have to show the opposite. What's the opposite? The opposite is you trying to find an impair number, because in this case we have a squared, which is a pair number. So don't a squared is pair. So we suppose that this a that we have here is impair. And how can we suppose this? Like I said, we're going to have a topic where we're going to be looking at functions. Our Mono or I will teach on pair and impair numbers. Okay, we're going to get to understand what really pair numbers and impair numbers are. So we say, okay, if we suppose that a is equal to 2a prime plus 1, if we make this pair a squared, we're going to say, okay, if this is a squared, we're going to put this in bracket, and then we're going to have square. So if we simplify this, it gives us 4a prime squared plus 4a prime plus 1. Okay, which is, in this actual sense, this becomes impair because we have a state is impair, which is here. Put into mind that if it's going to be pair, we're going to annulate because this is what is making everything here become an impair. We're only going to consider this function that is here, which is pair. Okay. On déduit donc A est pair. Donc on peut écrire A égalé à DA prime. If we don't have an addition of this, if we suppose that A is equal to 2A prime, ce qui donne DB au carré, which is here, égalé à 4A prime. If we annulate cette part ici, if we simplify and forget about this part here, which is making it become impair. So if we forget annuler cette part ici, ça veut dire que aussi ici, we're going to annulate cette part ici. If we annulate this part, we are only going to remain with 4a prime squared, which is going to be equal to a squared. So where is my a squared? I'll put 4a prime to the power prime 2, which is the one that I have here. A, we're going to say 2b squared is equal to 4a prime squared. We divide by what? We divide by 2. We divide by 2. It's going to give us b squared, which is equal to 2a prime squared. Okay, that's how it is. I'll get this question and put in my in the TD so that we can I'll solve it using weight. Okay.
Yeah. Thank you. Now, what's the meaning of prime and how we are having it?
Sorry.
The meaning of prime and now we're having the a prime here, like not understanding where it's coming from and the meaning, the use.
Okay, so prime that we have here it's a similar question that one of our sisters had asked. So here we have a is equal to 2a prime. If we just use a here, it will mean you're going to simplify this a and this 2a here. It will be the same. Okay, so if you want, you'd say, okay, I don't want to use a prime here. You can put x. So a prime is just a number that we don't want to be coinciding with this a here. No wonder we put an a prime here. Is it clear?
Yeah, I'm clear now. Thank you.
So two more questions, please.
Wait.
Yeah, I understand where the a means 2a prime, but where it says allo a squared 4a, that long fraction, the quad. Yeah, how come the last two are disappearing? That is the 4a prime and the plus 1. They're disappearing when we like finish up everything.
Okay, so I'll read this statement again. On no début donc A est pair. If A is pair, what is making this function to be a complicated paired function in this case is because we have an addition of a certain value. For example, if we are to reduce that this is a prime is equal to 1, we're going to have 2 1. So we're going to have 3. If we're going to have 3, we're going to have square root of 3. Square root of 3 is not going to give us a pair number. Okay, can give us a pair number. So we are going to. Okay, somebody's mic is on. Okay, so we deduce that we're going to remove this plus 1. reduce it in coincidence with the one that we have here. So it's like the last digits are the ones that bring us to become an entire number. I would suggest that if you wanted to understand this part very, very well, it's unfortunate that you haven't done pair and pair numbers. Yeah, it would have been good, or you'd have understood better if you did pair or impair numbers. So you make some research on pair and impair numbers. That's when you get to understand why this plus 1 and that this 4a prime plus 1 is being removed. But in general sense, the only thing that we consider is the one with the highest power. Okay, the highest power. That's the one that we consider. So in this case, for example, we go to 2a prime. The highest power we have here is with the coefficient is a prime, which is 1. So this that we have here, the highest power, the power that we have here can be 0. So we're going to annihilate some. Here, what's our highest power we have? We have our highest power, which is what? 2. So we annihilate that with the least power, and we only consider the one with the highest power. That's one that we assimilated with the a squared, which is it's got a similar power. We've got the power here, which is 2, and the power is here, which is equal to 2. I'll do this same question again. I'll solve it very, very well in the tip that we're going to have problem on Friday. Okay, so I can solve it step by step. Actually, I thought I did it with you, but like I didn't do it with you. C'est bon?
Yeah, I've understood. Thank you.
Just a minute. I'm still confused here. Why are you saying A is equals to 2A pair, and then here again you said 2B squared is equals to 4A squared.
Here I said A is equal to 2A prime. Yes, ma'am. So we only consider this first function with the same power. We've got A to the power 1 here. We've got A to the power 1 here. A prime to the power 1. So I've got similar power. So the same thing happens the same power. We've got A squared and we've got 4A prime squared. So we've got the same power. So here if we have 2A prime, which is for A, then your A squared, which because this function that we have here is this one here. We've got 2B squared. Your A squared that you have here, you see which one? Should we pick this one? We can't pick this one because it's got A to the power 1. We pick function with A squared. So A squared that we have here is this one. It's got a similar power, which is A 4A prime squared. Okay. So we are only going to consider, because it's A squared, it's A. That's what we develop 2B squared is equal to 4A prime squared. The A squared, which is coming from this part here. C'est bon? C'est bon?
Okay, fine.
You have seen it? J'espère. Okay. Donc, okay, in 10 minutes, we're going to have a pause. We're going to have a pause for 15 minutes. Then we'll do what we just will get back since we said late. We're going to finish at 18 hours, I think. Okay. Démonstration. Comme pour square root of 2, nous allons faire une démonstration par l'absurde. Suppose que, bon, c'est the same thing. I'm not going to do this part. You just write roughly. It's not very, very important.
I'm sorry, Ernest, to take you back.
Okay.
On top a bit, after we discussed that 2 square root is not a rational number, you said that even the pi is not a rational number, right? Down.
Example, yeah, pi is a rational number, yes. The pi is
yes, pi is not a rational number, but then after okay, number 1 says pi is not rational. Then number 2 says what exactly? I didn't understand this part.
Okay. Here we are saying le nombre pi 3,5 défini comme la circonférence de cercle. Okay. The number dual is the exponent function. This is an exponent function. So an exponential function also, which is equal to 2, you can get to a calculator and just press on E, you say equal to, going to give you this number. Okay, this is a constant number. Okay, so this one also is a irrational number because it's a consistent number. La base de l'exponentielle définit comme une somme infinie where E or exponential function is equal to 1 plus 1 over 1 factorial. You are going to get to analyze this when you look at the Vermont limit. So for now, just get a general view on it. Yeah, 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial up to 1 over k factorial. Okay, k which is going to be any number that you would want to put. So for now, just base yourself on the exponential. Like just know that E is it irrational number. That's the most important thing. Otherwise, when you start looking at the factorials here, probably people didn't do enough. You begin to confuse yourself. C'est bon? Okay. Et voilà. So we have, you can just try to read this through. It's exactly the same that I've been explaining on top. I want to really go into details in solving square root of 2. Yeah, you'll probably do, even at when you go to for this. I remember in my first semester, I just did this in 5 minutes and the prof didn't spend a lot of time. So probably it's not something very, very essential that you need to just get a general point of that. Square root of 2 is not a rational number. That's just a general point of view. If you want to go into details, you can probably get to solve this. I'm always here. If you are probably, if you try to solve this, you don't understand somewhere, just tell me. You all have my WhatsApp line, and then I'll be there to explain to you. And of course, we're going to solve this question in a TD. We're going to have. Okay. What else do you need to know? This is not very, very essential. Voila. Okay. We're going to take a pause for 10 minutes and then we come and continue. We're going to be looking at Majoran, Numéron, et partie bonnet. 10 minutes. That is at 17:10. We will start. C'est bon? If there are no questions, of course. Questions? Question? Pas de questions.
Yes, there's a question. What's TDS?
Sorry?
What is TDS? You mentioned something like TDS. What is it?
Those are travaux dirigés. Travaux dirigés, there'll be exercises that we'll be doing. So I'll be solving questions for you. So everything that we've learned in the course, I'll solve questions with you guys so that you understand more. And it's just like application of what we've done in the course using questions.
All right.
C'est bon?
Oui, c'est bon.
All right. The TDs that I'm going to be doing with you, you might find the same questions in your exam when you go to school. So be very, very careful, okay? There are a lot of where I solved a question and the same exact question that someone went to school and they wrote and they called me at night after writing the exam. So the same question that we solved with you doing some lesson Analyse came at 35 marks. And yes, I've worked on it. So be very, very careful. That very, very important to do. You never miss. Alors, bon appétit. 10 minutes. We go. Ça va être quoi? Ah bon? Malheureusement, je n'ai aucune idée concernant ça. Oui. Ça veut dire? Ah, d'accord, d'accord, d'accord. Ok, donc, donne-moi 30 minutes, 35 minutes comme ça. Je vais t'appeler. Oui, oui, oui. Pas vraiment. Pas vraiment, oui. D'accord, d'accord. Donc, à plus. Au revoir, au revoir. Ouais. Okay, we can start. Are we there?
Yes. Yes, yes.
Bon, I just saw a comment. Mr. Dasam Dwachura. Dasam Dwachura, what time is the lesson ending? You said later. I said the lesson at 16:45, and I'm so sorry for taking much of your time. Yeah, I not even taking much of your time is because if we waste a lot of time, it's you that are going to be affected. It's you guys are going to be affected. Yeah, so I'm trying by my possible. Just now, I wasn't even home when I was supposed to say, yeah, the problem is, I'm on a problem with internet, so I just had to come in. So let me just do my part, and I'll let you free. So, the board, just I'm going to that. I'll pass clear. So 30 minutes will be done, and 30 minutes I'll be done with my first part. So we start real numbers. I hope I haven't forgotten what natural numbers. So already we've looked at natural numbers, we've looked at integers, and we've looked at rational numbers. So now we're going to enter into real numbers. So real numbers can be considered to be in three aspects actually. So we're going to enter into real numbers by looking at the majorant, minorant, partie bonnet. Majorant, ça veut dire quoi? What is this? If I say majorant, what do I mean? Lawrence, what is majorant? Lawrence? Okay, Lawrence is not here. Jabez, what is majorant?
Maybe upper limit. Hello?
Voila.
Can you get me?
Yeah. Yes, yes, I can get you. Upper limit, très bien. Oui.
Yeah.
Katongo, majorant. Jabez has said upper limit, it's very, very correct. Katongo, according to you, what can be majorant? Okay, Katongo is correct. I'm just picking random because I don't really know you guys. So I'd have really preferred if you guys had put your real names on your face on the Zoom.
I can try. I can try. I can try.
All right, yeah. Just a minute, Katongo. There's people that are putting awkward names. This person that is putting entanglement. Can you just change your name and so that at least you...
Inshallah.
So player. Yeah. Yes, Katongo. You're saying something. We can try. I let you try.
Okay. I think majorant is a function element that dominates others or is greater than others.
Greater than others. Très bien. Means that you've got an upper limit. So it's a function that you have which has got an upper limit. It's actually in the same circle like our friend that said. Elisha. Okay. Wait.
Maybe I can say upper bound. We can just use a different language, something like that.
Upper boundary. Très bien. Okay, so before I continue, are we okay? I really want to be slow with you guys. Are we okay with natural numbers, integers, and rational numbers? Are we okay there up to now? Very, very important. I want to know. Are we okay there?
Yeah, well, okay.
Because I don't want 2 days somebody should come to my inbox and say, "May I didn't understand anything you taught." It's Amban. Because I've asked this question very, very much. Okay.
On the real numbers and natural numbers, just repeat on the part where you said about something like subset and all that.
So on the part for subset, this part here, oh, well, it's actually the same here. Here it's just like we are concluding to say we've got the first set of the numbers. Well, we've got a certain set that we have of natural numbers, and these natural numbers have got a subset which is integers. Okay, so the integer that we have as a subset is because we're looking at natural numbers and numbers that are from 0 up to probably infinity. So what of if in this same natural numbers that we have, we include numbers that are negative and positive at the same time? We develop integers. And out of these same integers, what of if we were to have things out of these integers that we have as fractions? We develop what? We develop rational numbers. Rational numbers, what of if everything that we have in rational numbers, we also, well, there's one that we have here, which are real numbers. Real numbers, we all know what real numbers are. We've got an inclusion of every set that we have of natural numbers. In that set natural numbers, you can find integers, you can find rational numbers, you can also as well find real numbers. That's the part that we're going to start focusing on. So in a general sense, we're just saying the set that you have is a set of natural numbers. And in this same subset, the set of natural numbers you have, we've got integers, we've got rational numbers, and we've got real numbers as their subsets. C'est bon? C'est bon?
Oui, c'est bon.
Très bien. Okay. So majorant. So la définition, on a majorant, minorant, partie bonnet. I can't really see any girls. Are the girls here?
Yes, we're
Yes.
Girls, this intake has got good girls. They don't have any questions. I guess things are very, very okay for them. Well, yeah. Okay. Girls ask a lot of questions, so I'm surprised this is other way around. Soit A, une partie de R. Number one, we have the real M. So the grown M or the capital letter M is the one that represents majorant. M étant majorant de A. Si pour tout A appartient à grown A. So we have M is a majorant if we have got a set A. So a set A can be either a set or maybe an interval. Okay. Or rather, it's better we just say we've got a set A. And out of this set A, a certain letter that is A or be a number. We don't want to assign it to a number. Normally, like I said, the first day that we did the analysis, I said we're going to be using a lot of letters. We avoid to use numbers because when you use numbers, it's like it becomes like a constant. Okay, so use letters because a letter can represent any different number. So in this case, we represent any different number with A. So we say if A belongs to a set of ground A, on A inférieur ou bien égalé à M. M which is the majorant. So the highest number that you have out of this set of A is your majorant. Very, very important. This question rarely misses in an exam. So if you don't understand this part here, you already have 1 mark or 0.5 marks out of the exam. Majorant, minorant, very, very important part you have to understand.
Sorry, can
This
you
one,
please?
Okay. Yeah, like I was saying, this one you'll find in exam. This one I promise you will find this question in exam. So you have to understand very well. I'll repeat myself. So M or ground M is represented by a letter majorant. Okay, a majorant. So a majorant, like what I've described this, we can describe as the highest digit in an interval or in a set. So for example, if you have a set of 1 up to 10, the majorant we get to have there is 10. Okay. So if we have a set, for example, A, and in that set A that we have, we've got a certain value or a certain letter or a certain number, which is A, and that A belongs to a set of the set A that you have, the petit A. If you want, you can put X here. We can say X belongs to a set of A. So we can say the majorant is the highest.
NS.
Oui.
Can you kindly repeat your explanation on this definition for majorant and everything else here?
Yeah, that's what I'm trying to actually explain right now. I don't know if my thing can open up. Okay, let me just try to write something so I can explain what I was writing. Okay, paragraph. Okay, so we have M. So I'm saying the real M, or M is the letter that we represent for majorant. Okay, so represent majorant by capital letter M. If we have a set, and in that set, we've got a certain number, which is in this case represented by A. And this A belongs to this set, and A is probably the greatest number in that same set. Okay, we can say A is less than or equal to the majorant. If we say A is less than or equal to the majorant, because of this equal to sign here that we have here, we can say the value of M is equal to what? The value of M. If we say A inférieur bien égalé à grand M, ça veut dire M is equal to what? We can say M is equal to what?
A.
Très bien. So it can be equal to A. Très bien, Ruben. So if we're saying majorant is equal to A, mean that A is the greatest digit that you have in the set A, and that becomes your majorant. C'est bon?
Oui.
Très bien. On dit que A est majoré si A a un majorant. So we say A is majoré if it in that set it contains a certain majorant, or it contains a big number. For example, I'll give an example. I have a set. If I draw a set of let me see. How this works out. Okay. If I draw a set from some, voila, that's my set that I have here. That's my set that I have here. And in this set, I have numbers 1, 2, and 3. If I ask the question, what is my majorant in this set? We've got 1, 2, 3. What's going to be my majorant in this set?
3.
3. Why is it 3? It's because it's the greatest number of this set that I have, which is this set A, and that becomes my majorant. So we describe this, everything that is written down here as in this situation that we have over here. C'est bon?
Oui.
Any questions?
C'est bon.
Yeah, there's a question. So, like, what's the difference between majoré and majora?
On dit que A est majoré. A is majoré. Si so we say A is majoré. We are saying A is majoré because we have got, I can say it's like we've got a certain number that makes it to be a majorant. Okay, so we can only say a set is majoré if it contains a majorant. Okay, it's like we can say a set has got a high value if it really contains a certain high value. You cannot just say a set has got a high value if you don't know that it really, in actual sense, it really has a certain value. So a majoré here is like la norme. Okay, so saying A can be called, it can be called a set with a high number, or it contains a certain digit, a great digit in it, if for sure we have that digit in that same set. C'est bon?
Oui, c'est bon.
Très bien. So the majoré that we have here, so the opposite of a great, the greatest digit is what? It becomes what? It becomes the minorant. So minorant is actually the contraire de majorant. C'est bon. So we have got it. Minoré de A, si pour tout A appartient à A, on a M inférieur ou bien égal à A. Ça veut dire the least value that you're going to have in that subset. On dit que A est minoré si A une minorant. Ça veut dire that, for example, that thing, the set that I'm actually from giving you, the set that I'm actually from giving you, we had 1, 2, and 3. We can find that the minoré that we have is what? Is it 1? So in that sense, if a question will come, we'll say, okay, our minority that we have in this set as that is contained is 1. We're going to look at this more as we do suites, but just have to keep up with it. The definition that we have, very, very essential, this part and this part. Sometimes in an exam, they'll ask you a question like, étudier la majorant et minorant. Every time we are going to study that, you have to give this definition. Very, very important. You start, for example, if they say, they give you a sequence 1, 2, 3, 4, 5 up to 6. They ask you trouver la majorant. You have to start. Pour trouver la majorant, le réel M qui est défini comme si pour tout A appartient à A, on a A inférieur. You have to write this down. You want to gain marks. It's a very, very important definition. So every time you are going to be asked questions on majorant, make sure you bring down this definition here. It's supposed to be in your heart. It's very, very simple to touch or to capture. So this definition, don't ever forget this in your life. Those that are doing engineering, SVT, BCG, any course, business, everyone that is here, don't. This is very, very essential. So we'll play. Okay, keep this definition in your heart. Never lose it. Okay, the last part that we have is si la part A est majorée. So if we have a part, meaning that we have got an interval now. If we have a part that is got it, a majoré and it's got a minoré, on dit que A est borné. So definition of a borné is we cannot define a borné if we have a situation whereby we have got a majoré and minoré. C'est bon. So only in a situation where we've got a minoré and the where we've got a minoré and the majoré, that's the only time that we can actually have a borné. So I want to look at le suite borné et tout ça, but pour le moment, il faut bien comprendre c'est quoi majoré, c'est quoi la minoré. That's what is going to help your life get to understand and analyze a lot of things as you start solving TDs. Okay. On continue, s'il n'y a pas de questions. If there are no any additions.
There's a question, boss.
Yes, bosses.
So we can't have bonnet without majoré and minoré.
No, we can't. We're not going to have a bonnet.
Now this thing it's a bit confusing. On the bonnet here, like a certain group, won't it always have like a bigger number and a smaller number, a bigger variable and a smaller variable?
Sorry, I didn't get you clear.
I meant the part of bonnet.
Oui.
There can be an instance where there's not the you said minority?
Yeah, well, with the majority.
Majority, like a bigger number and smaller variable.
No, in that case it will have to actually depend if I go to if I actually go to your question. I think your question is saying if you have got a bigger value, every bigger value that you're going to be having is already a majority, and every small value that you're ever going to have is already going to be assimilated to a minority. So already in that interval that you're going to be having, and that set that you're going to be having, automatically it's going to be A is going to be set bonnet. Why? Because it's going to continue. It's the same thing. For example, you have 1, 2, 3, 4, 5, 6. Maybe we say B is equal to 1, 2, 3, 4, 5, 6. Already in that interval, that range that you already have, there's already a small value and there's already a big value. Ça veut dire que déjà c'est une bornée because you have a certain small value and a certain big value already in that set. I don't know if I really understood your question, but yeah. My network is kind of getting bad. Est-ce que c'est bon?
Mr. Ernest.
Oui.
So, if I got you clearly, what you are saying is a bonnet is simply a set, but majority and minority.
I can't get you thing.
What I'm saying is bonnet should be a set, then majora and minora should be the members like.
You can get Ruben, because I can't really get him.
Yeah, I can get him.
Yeah, Ruben was like, your conclusion is that the bonnet is a set having majora and the minora.
Wait, if I got you well, you are saying my conclusion is we can only describe bonnet if we have majoré and minoré. According to the definition we have here, si la partie A est majorée et minorée, on dit que A est bonnet. We can have exceptions, yes, but in a situation like this, the only thing that we have to capture is if we have a part that is majoré and a part that is minoré, where we should be allowed to say, okay, the set that I'm having on the end of what I'm having A is bonnet. That's what we have at the table. We're going to be looking at exceptions. Analyse has got everything that you solve. It's got an exception. On suites, we're going to come back to the same part, but for now, just put to mind A is majoré. If A has a majoré and minoré, we're going to say a bonnet. Bonnet is also divided into two things, okay? Bonnet, this bonnet that we have here, it's going to be divided into two things. We're going to have what we call bone superior and bone inferior. Bone superior is going to be affiliated to majoré. Bone inferior is going to be affiliated to minoré. I don't. That's why I don't want to enter into details very much for now because I'll start confusing you. So for now, put it to rest to say A, si A est majoré et minoré, on dit que A est bonnet. Why? Because it contains bone inferior and bone superior. C'est bon?
All right. Can there be a situation whereby a set only has a majorant without having a minorant?
It will depend. Yeah. Bon, that one again it will depend unless you have got a constant value. Okay, that can only come when you have got a constant value. So if you have a constant value, for example, you've got a set of 0, 0, 0, 0, 0, 0, 0, 0, 0. Of course, there it's going to be kind of complex for you to find majority and minority because you've got a consistent value. Okay.
One more question.
Hello, boss. So can you give an example for bonnet?
Example here. For example, I'll take this interval. I'll take this interval that we have here. You can now see this one. X inférieur ou bien égalé à 1. X inférieur ou bien égalé, bon, supérieur égalé à 1, inférieur ou bien égalé à B. Between the two, A and B, which one is the majority?
It's A.
B.
Oh, B majority.
A, the majority between the two. Majority is going to be majority.
B.
It's B. So ici, this is the definition here. C'est ça, ici. You've seen this part here, là, ici. Voilà. It is the one that is here, where there is A, we just put X. So your majority becomes A is B. And this part here that you have here is the one that is here. So your minority that comes here, see? A. Est-ce que c'est clair?
Oui, c'est clair.
Très bien. C'est comme ça.
So provided that the set has,
you want to say something?
Yeah. So provided that the set has more than one member, it automatically qualifies to have both the minora and the majora.
Oui, bien sûr, bien sûr.
And you also said
if we have only a constant, if we have only one digit in a set, for example, 00000, then in that case, what do you have? Is it a majora or a minora?
We call that kind of set as a static set. A static set means that it's a set that's just static. It just contains one value. So we can't have a minor and we can't have a majora, because it's going to go against the definition that we have of majora and minora. Always you have to go with the definition that we have here. So as long as it's against this definition that you have here, then it's not a set that you can try to do to define which one is a majora and which one is a minora. The static set. C'est bon? Okay. Okay. The girls, are we okay? Jusqu'à maintenant?
Oui.
Okay. Okay. On va continuer alors. Définition on interval. Okay, we define an interval and a segment. Soit A et B, des réels tels que A inférieur ou bien égalé à B. On note A et B l'ensemble des réels X tels que X inférieur ou bien égalé à A, pardon, supérieur ou bien égalé à A, à la même fois X inférieur ou bien égalé à B. C'est un intervalle fermé. So if we have an interval, these are closed intervals. We remember those things from Zambia. Yeah, like in my memory tells me, right? We've got a closed set. So a closed set is this one here, where I've got the brackets that are closed, and we represent this closed set by having this type of interval: inférieur ou bien égalé à, inférieur ou bien égalé à. C'est clair? This is what we call a what? A closed interval. This is a closed interval. So we have égal ici et égal ici. On s'appelle ça closed interval, and we represent this by closed brackets. On dit aussi que A et B est un segment. So we can also, of course, say that A and B is a segment because we have got a certain interval that's going to be ranging here. We've got a certain range, but it's a well-defined range because it's a closed interval. Okay. On note an open set A, open set B, l'ensemble de real X such that it's not equal. Why is it not equal? Is because it's giving you an option. This means that it will go to B, probably C, D, anything. It's an open set. You can add any different type of number that you can want in this set. It also applies the same thing here. It can be either negative, or it can either be the positive. So we present this by not adding the equal sign because it's an open set. We have got X is less than A, and X is superior to A, X inférieur à B, which is a set that is an interval. Okay. Donc, on définit de même les intervalles mixtes ou bien semi-ouverts. So we can also define some intervals that are mixed, or we can call them semi-open. So we close it here and we open the other side, or rather we can open it here and we close it the other side. We call these mixed intervals because we've got an interval that is closed, a part that is closed and open at the same time. On introduit aussi le symbole infini. We look at this symbol infini. We note, so for example, in a case whereby it's an empty, it's an open set, we normally say we close a positive infinity because it's going to the positive side, so it's positive infinity. And we can represent this by saying A inferior ou bien égalé à X. The only value that you have which is estimated here is A, which is a closed interval. And then we have got negative infinity and a closed set. Ensemble de X tel que X inferior ou bien égalé à A, which is the least value that we're going to be having in this case is what? Is A. That's the least value that you have. Okay. So in actual sense, that's what, so here we're just looking at intervals, an open interval and a closed interval, and also looked at a bit of a segment. A segment is described from when you have an interval that is closed according to this. And if you have an empty set, for example, in this situation, we're going to have positive infinity this side, we're going to have negative infinity going the other side. C'est bon? Questions?
Yeah, but there's a question here. Like I don't really understand what you mean by closed interval and open interval.
A closed interval. Closed intervals, look at this. The closed intervals are the ones that contain the equal sign down. Open intervals don't contain any equal sign. I mean that these are the open intervals don't contain any sign. I mean that it's an open. A can be any number. It's open. But in this actual sense here, we are saying X contains only a specific number, which is the A, or X contains a specific number, which is only B.
Can you try to repeat on the part where you explain about the infinity and all that?
Sorry?
I didn't get you on the part where you're talking about the infinity.
Which part?
Where you're talking about the infinity.
The infinity. All right. So I was talking about the infinity. So the infinity here comes about because this is an open set, okay? Because we have got an open set here. Well, okay. For example, here we've got an open set. An open set means that this you can either put C, D. It's an interval that is ranging up to infinity. So when you move to this side, it's positive infinity. Okay. So that's a set that you're going. That's a set that we have in this sense actually. So we say positive infinity if we have got an open set that is opening to your right. We have got negative infinity if it's a set that is opening to your left. Meaning that you can have any sort of number until positive infinity. You can have any set of number until negative infinity. That's how we bring about positive infinity and negative infinity. C'est bon?
Oh, so
Alright,
A
thank
of
you.
Oui? You're saying something?
No, thank you. I've got it.
All right. Okay. Let's go much. Okay, let me just conclude. Okay, so let's just conclude we do these two theorems, and then we can call it a day. On Friday, pardon, we're going to do a TD. So we look at the first theorem. Bon, okay, an exemple, we've got 1.23 pi. Le pi sont des majorants du segment 0 et 1, because so we're saying P is a segment of 0 and 1 because we've got 1.23 which belongs to this set that we have here. A est un majeur de A de ça. So in this case, we have an open set 0, 1. So we're saying 1 is a majorant de A of this type of set that we have here. L'intervalle closed A a positive infinity n'est pas des majorants. A set that has got this kind of value has got no majorant. Pourquoi? Because you cannot have a majorant as positive infinity. It's got no specific number. How do you define majorant? You have to come back to your definition again. Very, very important. We said A is less than or equal to M. So in this case, the interval that you're going to be having here is not less than or equal to here. Okay, it's an open set. So this cannot be a majorant. J'espère que ça c'est clair. Continue avec ça. So I've got the first theorem that we have. It's called the propriété d'arithmétique. Donc soit x et y des réels. So soit x et y, which are real numbers, and these are greater than 0, meaning that we can have 1, 2, 3, 4 up to infinity. Alors, il existe un entier n tel que n fois x, y est supérieur à x. Okay, so therefore we can say there exists an n such that n times y is greater than x. So if we have, for example, x here, in actual sense, we're going to say every time that we're going to be multiplying this natural number that we're going to be having here by y, it becomes greater than x. That's according to propriété d'Archimède. Nous ne démontrons pas cette propriété. We're not going to show this property. Elle dit qu'on fasse assez de pas de longueur et on dépasse x. So saying this one normally just makes us understand that every time you're going to multiply a certain number that you have here, because we're saying it's greater than x, it should never be the same with x, because you're increasing bit by bit. Okay, you're making it become large. De l'U, avec notre définition de réel, la propriété d'être médian est évidente, ce qui est loin d'être le cas quand on définit un nombre réel de manière intrinsèque. Ça veut dire que this one now is helping us, propriété d'être médian is one that is now actually helping us to say, we've got an increase of every certain type of number. So in this case, we are saying every real number has got a certain way that it increases. Okay, so an increase of that number is what makes us to have, for example, a number that is minoré and a number that is majoré. Okay. Voila. So if you remember well, I talked about the bonnet ici. Here ici, le bonnet. We talked about the bonnet. So the bonnet here now, look at this, where we have what we call bone superior and bone inferior. If you didn't understand what majoré and minoré is, you're not going to get to understand this, because this one actually is the same objective that we have when you're looking at bone inferior and bone, majoré and minoré. Same thing. This don't miss in the exam. Very important. Minoré, majoré, bone superior, bone inferior. Yeah, you bear me witness. One or two, if not 45 of you are going to call me and say, it actually came in my exam. Donc, soit A une partie non vide de R. So if A is not a part, that is, it's not an empty set with real numbers, or the plus général de ensemble est muni de ordre total. So we have got a total order of less than or equal to. Getting back, if we have this already, we know that we can have, we have the right to have majorant and minorant. On appelle bone supérieur de 1 le minimum de l'ensemble des majorants. So the minimum number of the majorant is what we call bone superior. And the maximum number of minorant is what we call bone inferior. The minimum number of the majorant is what we call bone superior. And the maximum number of, or the maximum set of the minorant is what we call bone inferior. Very important thing to understand. Donc, avant d'énoncer le théorème d'existence de la bone supérieure d'un R, montrons que la bone supérieure n'existe pas toujours. On se place dans les nombres irrationnels l'une de l'ordre naturel. This question actually was a question asked in my exam. So I'm going to solve this in the TD. And I think you're all tired and I've talked so much. So we're going to pause here on bone inferior and bone superior. And this part I'm going to put in the TD and I'm going to solve it with you guys. So we're going to find the bone superior and bone inferior. Of course, before finding that, we're going to find the majorant and minorant for this. You can try to work out this question. Yeah, you can just try to work it out from what we just described here. Minorant, majorant, try to put in practice. I'll send you the 3D questions tonight so that you can start working on them. So I'm very free normally from 14 to 18. So you can text me during this time normally, and I'll be there to respond to you if you solve something and you need clarity. Just start toujours là. If you haven't understood a part in the course, you can just text me. Probably maybe we can find some time that I can go through with you and make sure that you understand. Don't remain behind. Make sure. Ça fait. Donc, je ne sais pas, est-ce qu'il y a des questions jusqu'à maintenant?
Is this video going to be posted on YouTube as well?
Sorry?
Was it recorded? Is it going to be posted on YouTube as well?
I think, yeah, it's been recorded. It's been recorded. in a recording thing there.
All right, thank you.
Ok. Oui, d'autres questions?
Yeah, there is a question before you close.
Oui.
On the first theorem, what does the n represent?
The first theorem. It represents a what is a natural number. N natural number. So we've got 0, 1, 2, 3. So the n that represents just the same number that we got here. When you started looking at the first, that's the first part that we're looking at. Where is it? So we actually get to say all these things are connected. Yeah, it's this number that we have here, the n, that we admitted that it's going to be an increase. So that's an n that we're still using here. C'est bon?
All right, c'est bon.
Très bien. Oui, d'autres questions?
Yes, boss, à peu près une étape so.
Yes,
back.
Yes, Naruto. Teddy, you are speaking?
Yes, go back just a bit up there.
On what part?
Where we had yeah, there. No,
yeah.
Get back. No, get back. The previous one. Again. Yes, there.
Oui.
No, not there on the majora, just a bit up.
A bit
where
up.
we had, yes, there, where we have the N, Z, Q, I.
Okay, here.
Yes.
Here I was just saying we've got natural numbers, okay? So I've got natural numbers. In those natural numbers, we find integers. We've got a subset of integers, we've got a subset of rational numbers, we've got a subset of real numbers. Out of these same natural numbers that we have. This is just a general thing to talk about what what natural numbers are, what integers are, because integers actually are gotten from natural numbers. So it's just like we say, okay, we found negative and positive number at the same time. We call them integers, but in actual sense, they all came from the same group of natural numbers. That's what we just try to describe here. C'est bon?
Oui, c'est bon.
Okay. Any other questions?
Yes, I have a question.
Yes, Harold.
Could you kindly repeat the explanation for bone superior and bone inferior?
Okay. Okay. So bone superior, we say bone superior. This is the minimum set of the majorant that you find. Okay. So it's like you've got a set of numbers or a set of objects that you have, which is your majorant. So the minimum number that you actually get out of that same set is what we call the bone superior. And the bone inferior is the maximum number that you get. For example, if you have -1, -2, -3, and you say this is a set of your minorant, okay, the maximum number that you have there is what is -1. So -1 becomes your bone inferior. Okay, we're going to, when you do questions on this one, not I didn't want to put a lot of pressure on this part, you're going to understand better as we solve this question here. So for now, just know the definition. Bone superior is a minimum set of majorant of A, and bone inferior is a maximum set of minorant. That's Okay, pardon moi. I don't know what happened. Notice my. Do you still have any questions? Do we still have any questions? Yes, yes, bosses.
Yes, I have a last question. So, does it mean that in a simple set, just a simple set, maybe of 3 numbers, we can't have the bond superior, we just have the majora and the minora, just that?
Where there's majorant, we're going to have bond superior. Where there's minorant, we're going to have bond inferior.
So you are saying the majora is same as the bond superior?
No, it's not the same. The bond superior is the minimum set of those majorant. And I'm saying when you solve questions, you're going to get to understand what the difference between the two.
Okay.
Okay.
D'accord.
Okay. Any other questions?
Yes, I have a question. On the what's his homework part, are we going to prove that equation is not a bond superior or what?
Bon, ici, on considérait la partie 1, x appartient à nombre rationnel, x squared. In actual sense, you remember, you know where this is coming from, right? This is someone saying what? X is less than what? Square root of 2. Is square root of 2 a natural number? I mean, a rational number.
No.
Voila. So that's what should start making you to think before you solve anything. Alors, A n'est pas de bond supérieur dans ça. Pourquoi? Because when you start proving, when you get to solve this part here, that's when you want to understand, oh, actually A then have a bond superior because of this. So it's not going to have, you can only tell this when you understand actually what is really going on with the question that you have there. C'est bon.
Oui, c'est bon. Merci beaucoup.
De rien. Est-ce qu'il y a plus de questions? D'accord. S'il n'y a pas de questions, we'll continue doing the questions, and I hope you all had fun. Even if it was very rough for us today to get to make this class. The next lesson I'm going to be with Mono. I won't be around. So probably just try by all means to ask any questions to her. She's there to answer you guys. And if I'll be there, I'll be also there to help her answer any question that you have. Et bonne nuit. Merci beaucoup. Okay, somebody's saying kindly share some homework. I'll send in the group. I'll send in a group now. Yes.